Hello and welcome to the next lesson in the radioactivity topic. This lesson follows on from the key things that we learned last lesson about types of ionizing radiation. So now we're looking at how those types of ionizing radiations are formed through the process of radioactive decay. So today's lesson is radioactive decay. Okay, let's get our brains on track. I'm hoping when you see them diagrams there that they should hopefully mean something to you from the last lesson on types of ionizing radiation. You notice that Bart's joined us again this week. He hung around after the last lesson. He actually said that he finds all this stuff on nuclear physics quite interesting. So nice one, Bart. Stick with us. So task there, use the diagrams to compare those types of radiation we thought about before. How are they different? How are they similar as well? How much can you recall from the last lesson about those diagrams? And an extension. One of the types of ionizing radiation that we briefly mentioned last lesson is missing from that. So can you work out which one is missing? Have a think about it. I'll share my thoughts with you in 3, 2, and 1. So clearly we have got an alpha particle out at the top, 2 yellow protons, 2 orange neutrons. Next to that, we have got a beta minus particle, which is an electron in effect. And then next to that, we have our positron that we came across last lesson. We'll be coming across them a lot more in this lesson. And then next to that, we have a gamma wave being represented there by the squiggly line. Anybody remember which type is missing from that? Go on, Bart, lad. Well done. It is. It's neutron decay. And again, we'll look at that one in a little bit more detail towards the end of this lesson. Okay, quick look at the objectives at the start. We're kind of covering them all at once as we go through the types of decay here. So again, we need to be able to describe the process of alpha, beta minus, beta plus, and gamma decay. I'm putting the symbols there because you need to get used to them and know what each one stands for. And don't forget there's neutron decay as well, as Bart pointed out on the last slide. So for each of those, how do they affect the atomic number and the mass number of the elements or the nuclei of those unstable elements that are decaying? What happens to the nucleus after one of those decay processes? And we're going to tie that together with nuclear equations for the mass and charge of the elements that are formed as a result of these types of radioactive decay. Quite a lot to get through today, folks. Really important lesson in this topic. Don't forget, you're going to need to take notes on this slot. So we'll start with alpha decay. I'm going to show you a little animation at the start to give you an idea. So we've got a plutonium nucleus, and again, mass number 239, and we can see that it is emitting an alpha particle as part of a nuclear reaction. And again, you'll notice there that there are also some gamma rays produced. More on that later. These are the key points for alpha decay. So when an unstable nucleus, as we saw before, undergoes alpha decay, its atomic number and its mass number are going to change. Think about it. If it's just ejected an alpha particle, which has got 4 units of mass, 2 of which are protons, it's going to become a different element. So literally, by these processes, one element is changing into another. So I want you to think about this. How would alpha decay affect the atomic number and the mass number of the new element that's formed as a result of another element decaying by alpha decay? Have a think. I'm hoping you're okay with this idea that if it's lost 2 protons, the atomic number goes down by 2. If it's lost 2 neutrons as well as 2 protons, and don't forget each one of them has a mass of 1, then the mass number must have gone down by 4. Show you a diagram to help you with that. So again, looking at uranium here, uranium-238, another unstable isotope that will undergo alpha decay. So there's the parent nucleus, as we call it. There's a decay event going on, and an alpha particle is emitted. And then what we have there, and we refer to it as a daughter nucleus that's formed, we've got there thorium-234. And again, be really clear that the atomic number of thorium is 90, whereas the parent nucleus, the atomic number was 92. That's gone down by 2. Same if you look at the mass number. It's gone down from the mass of the uranium isotope 238 to the mass of the thorium isotope 234. A lot of important information there. Make sure you made a clear note on it. So let's, as that says, link that to nuclear equations, which is what you're going to see in an exam question. They're not going to give you diagrams, or if they do, they're going to link it to a nuclear equation. So that's the diagram from the last slide. How would it look as an equation? I'll talk you through this one. So we've got our parent nucleus, our uranium-238. There is a decay event, as indicated by the arrow. We have the helium nucleus emitted, the alpha particle. And as a result of that alpha decay, we have the formation of our daughter nucleus, thorium-234. So again, make sure you're clear on that. It's a nice example, make a note of, because on the next slide, I'm going to ask you to work through a few on your own. Just want to squeeze in another quick example for you of alpha decay. This one showing radium decaying to radon. It mentions its half-life there. Again, half-life we'll look at in more detail in the next one of these lessons. Again, the radon you might hopefully remember from what you've done before on background radiation. Of course, radon gas being one of the biggest sources of background radiation in the environment. Okay, your turn. So 3 questions there, 3 nuclear equations showing alpha decay for 3 different unstable isotopes. It's your job to work out the mass and atomic numbers of the daughter nuclei. Off you go. Here's the countdown in 3, 2, and 1. So for our daughter nuclei at the top, francium, the mass number will have dropped down to 219. That's 4 away from 223. And of course, the atomic number will have dropped down to 87. Of course, 87 is the atomic number of francium. For the daughter daughter nuclei, californium, CF, again, the mass number there is 239 and the atomic number 98. Hopefully you're getting the hang of this by now. Osmium, unstable isotope of, again, mass number 186 and atomic number 76. So just check your answers on them. Hopefully you were okay. So that's alpha decay. So we're doing well. We're on to beta minus decay in this instance. Now have a look at the animation. Obviously we'll work through it, show you plenty of examples, but you'll notice that we have got helium there decaying to form lithium. Now, as it happens, we have a neutron that turns into a proton as a beta minus particle there, the yellow dot is emitted from that nucleus. So let's have a look at this one, beta minus decay. Key information for beta minus decay coming up. As it says there, when a nucleus undergoes beta minus decay, literally one of its neutrons turns into a proton and a beta minus particle, an electron, is emitted. Little animation that shows that. There we go. We have a neutron turning into a proton, and we can see that little electron, the beta minus particle, being emitted. So the symbol we use for a beta minus particle is there for you. It's a little e. The 0 represents it's almost 0 in mass, and the -1 shows it's got a -1 charge. So how would beta minus decay affect the atomic number and the mass number of the daughter element that was formed? Have a think about it. If a proton has been formed, then what must have happened to the atomic number? Hopefully you're okay with this idea. The atomic number will increase by 1. Now, because a proton has the same mass as the neutron that it formed from by beta minus decay, there is no change in the mass number. Very important that. So we'll look at an example, carbon-14 undergoing beta minus decay. So there we've got our carbon nucleus. Again, carbon-14, unstable isotope of carbon. We'll think about that in a lot more detail in the half-life lesson. And again, it undergoes beta minus decay. that particle is emitted from the nucleus, and as a result, the daughter nucleus is nitrogen because it's now got an atomic number of 7. And again, nitrogen has an atomic number of 7. So literally, carbon-14, when it undergoes beta minus decay, that carbon atom turns into a nitrogen atom. So let's look at this in the form of a nuclear equation. There's a diagram from the previous slide. So we've got our parent nucleus, the carbon-14 nucleus, and again, the decay event happens, and we know that a beta minus particle is emitted. We know as a result of that, that a neutron has turned into a proton, and therefore nitrogen 14 has been formed. Again, be really clear on that. There is no change in the mass number, but for beta minus decay, the atomic number goes up by 1. And in physics, you don't get much simpler rules than that. If it's beta minus decay, you add 1 to the atomic number. Dead easy to remember. Just throwing in another example there for you. This one shows deuterium undergoing beta minus decay to become helium. The V minus there represents an antineutrino. Thankfully, they don't bother us with things like that for GCSE physics. Your turn again. Practice makes perfect and all of that. So can you have a go at those nuclear equations for beta minus decay? Remember your simple rule. If it's beta minus, you are adding 1 to the atomic number. Off you go. Count down in 3, 2, and 1. So in our first example, we end up with thorium 228, and the atomic number has increased by 1 to form thorium. Second example, we end up with lithium 6 because, again, the atomic number has gone up by 1, lithium having an atomic number of 3. Potassium 42 decays to calcium 42, and again, calcium atomic number 20. Hopefully you were okay on them. Just check through your answers. Hopefully we're ready to move on to the next type of decay. We are motoring along now, folks. We are now on to beta plus decay. So animation coming up. There we go. So we start off with fluorine 18 and we end up with oxygen 18. So what's different with the beta plus decay as opposed to the previous beta minus decay? I'm sure you can work it out before I go into the detail. Have a little bit of a longer period of time to have a look. You might even be able to work out what the V is based on a little bit of information I shared previously. So, beta plus decay, in effect, is the opposite to beta minus decay. In this case, what happens in that unstable nucleus, a proton turns into a neutron. There we go, if you caught that. Here we go again, proton, positron emitted as it turns into a neutron. So, how would beta plus decay affect the atomic number and the mass number of the daughter nuclei formed? Remember, I said it's the opposite to beta minus decay. So have a quick think. Well, clearly, if we have had a proton turn into a neutron, the atomic number must have gone down by 1 because there is 1 less proton in that nucleus. Again, the mass number will not change because the mass of the neutron that was formed was the same as the proton that it formed from. Let's have a look at an example. So we've got palladium-230 undergoing beta plus decay, and there's our unstable parent nuclei. There's our beta plus particle emitted, the positron. You can see the symbol there for it underneath. It's the same as your beta minus particle, but obviously that little one's got a plus there to show that it's got a positive charge. And there's our daughter nucleus of thorium-90. The atomic number has gone down by 1. The mass number, again, is unchanged. So key information there. Make sure you've made clear notes. Okay, so let's look at a nuclear equation for beta plus decay. So again, example, as we saw on the previous slide, we've got our parent nucleus of palladium-230. There is a decay event in which a beta plus particle is emitted, and as a result, we've got the formation of thorium-230. So again, let's remind ourselves the atomic number has gone down by 1. So that beta plus particle was emitted as a proton in that palladium parent nucleus turned into a neutron. Be very clear on that one. In beta plus decay, again, proton turned into a neutron, so therefore the atomic number has gone down by 1. That's a dead simple rule there for you as well. Again, if it's beta plus decay, you minus 1 from the atomic number. I'm throwing in just another example there for your information of nitrogen-13 decaying to carbon-13 in this case. Again, you'll notice the beta plus particle is emitted, and again, we've got that B there. Again, you might have an idea what that is from previous information. This time it's a neutrino, not an antineutrino, because it's not got the minus sign over it. But again, as I said before, you don't need to know about them for GCSE physics. You've got enough to know about. Time for you to have a go. So some examples of beta plus decay there. Please could you work out the mass number and the atomic number of the daughter nuclei? Off you go. Countdown in 3, 2, and 1. So no change in mass number there. For the first one, atomic number has gone down by 1. Same process. And again. And as we can see, hopefully, that process there, beta plus decay, we have a decrease in the atomic number. Could I say at this point, alpha, beta minus, and beta plus decay, they're the 3 ones that come up the most in the exam. On the next slides, I'm going to go into a little bit of detail on gamma decay and neutron decay. They come up less frequently, but we're going to cover them nonetheless. But again, I'll stress, alpha, beta minus, and beta plus, you must be able to do the nuclear equations for them and discuss what's happening in the nucleus in each case. Gamma decay then. Have a look at that. And again, here we go. Has the element changed? Has its mass changed? I'm hoping you're saying no there. Again, recall that key piece of information, gamma waves. Well, they're waves, aren't they? It's electromagnetic radiation. They're not particles, and therefore they are massless. You know, they can't affect the atomic number or the mass number. So why do we get gamma decay then? Let's have a think about it on the next couple of slides. So there's an example of beta minus decay we've already looked at. And again, we've got that formation of the daughter nucleus of palladium-234 there. Now, what you often get is a state where there is still excess energy left in the nucleus after the decay event, and we can refer to that as being in an excited state. So we've got it there referred to as an excited daughter nucleus. Now, as a result of that, it emits gamma waves to reduce that excess energy. So we say that the nucleus de-excites to the daughter nucleus of palladium-234. So again, it's exactly the same in terms of its atomic number and its mass number. It's just there's been an alteration in the energy level within that nucleus as a result of the gamma wave being emitted. So as we said on the previous slide, gamma rays are emitted as that nucleus undergoes rearrangements in terms of its energy level as it readjusts to a more stable, lower energy state. So there's no change to the makeup of the nucleus. There's no change to the mass or atomic number. Let's look at an example. We've got cobalt-60 there, decaying by beta minus decay. So we know that we add 1 to the atomic number, so we form nickel-60, atomic number 28. Now that's still unstable, and as a result, a gamma ray is emitted. The little star symbol by the nickel shows that it's unstable, and therefore the gamma decay also occurs. I just want to stress with neutron decay, I've not seen it on a GCSE paper yet, but you never know. It does say in the syllabus that you need to be aware of neutron decay as one of the 5 types of ionizing radiation. So that little animation shows nicely a neutron being released by the fusion of 2 isotopes. Okay, So clearly, neutron decay involves the emission of a neutron from an unstable nucleus. Now, we largely associate that with processes of nuclear fission and fusion. We'll not go into that one in this lesson. Again, neutrons are highly ionizing. I'm not going to tell you why. You might want to find that one out for yourself. Answers on a postcard, please. So how do we calculate neutron decay from nuclear equations? So let's have a look at those two examples. Again, be mindful, the symbol there for the neutron, it shows that it's got a mass of 1. And again, there's no charge because it's not a proton, so the 0 represents the fact that there is no charge. Have a go at those two. I'll talk you through the answers in 3, 2, and 1. So for the helium, we'll do that one first. Because it's lost a neutron, and that's 1 unit of mass from the nucleus, the mass number goes down by 1. But there is no change to the atomic number because there are still 2 protons within that nucleus. For the decay of nitrogen-17, again, a neutron is emitted, so it's still nitrogen, but it's now nitrogen-16. So it's still got an atomic number of 7, but its mass number has gone down by 1 as a result of that neutron being emitted. Here's one for you. The FYI there says that this is for your information, so it's not something you need to remember, but you should be able to work it out, really. Why are neutrons more penetrating than gamma, even though a neutron is a particle and gamma is an electromagnetic wave? Why are the neutrons more penetrating, as we can clearly see from that diagram? I'm going to freeze it and have a think about it. I'm going to click up the answer in 3, 2, and 1. So they are more penetrating, and hopefully you got that idea. It's because of their neutrality. And this means that they're not deflected by electrical or magnetic fields. However, gamma is an actual electromagnetic wave itself. So as a result of that, they can be deflected if they come into contact with electrical or magnetic fields, and therefore some energy is lost in those deflections. So yeah, neutrons are more penetrating than gamma rays. Just want to share a couple of things. Just watch this. So what this is showing is the decay of uranium-238. And again, I'm stressing there, this is a process that happens over millions and millions of years. Shortened it down to a very short space of time. Now, what it's doing is it's introducing this idea of a time scale for the decays, and that's leading us into half-life, which I want to cover with you in the next lesson. But again, you can't really understand half-life unless you've understood what we've covered in this lesson and the previous lesson on types of ionizing radiation. So I'll let that run one more time. Right, we've got a nice animation here, again showing something similar to the previous slide, the decay of polonium to form lead. Now, in that previous slide, again, we also saw the formation of lead being a stable element. Now, in this case, obviously, over a period of time, it doesn't specify on the scale, the polonium will all eventually end up being lead. Now, the curve that we can see there is a half-life curve. And again, every unstable isotope of every element has its own half-life. And again, I'm stressing there, some of them are very long, some of them are very short. I'm just going to share a little bit of information with you on that on the next slide. I'll stress this is for your information only, but again, it does link us nicely to what we'll be looking at in the next lesson. So we've got a decay chain there of uranium-238, and ultimately it will decay to lead-206. But we can see there is a hell of a lot of decay processes of alpha, beta plus, and beta minus in between the uranium and the lead. So have a quick look at that. As I said, it's for your information. You certainly don't need to memorize it all. But again, if you look there, I've given you the one for the uranium. its half-life is about 4.5 billion years, and it's knowing about the half-life of these unstable isotopes that allows scientists to actually put accurate dates on the Earth. So again, it's been very useful to science, this idea of understanding the half-life of radioactive substances. More on that next lesson. So you made it till the end. Thank you very much. We, as I said, covered a lot of important stuff for this topic in this lesson. You really do need to understand it, so make sure you are clear. Once again, thank you very much. I'll speak to you all soon.